Hello everyone, my name is Siddharth Gupta and I'm an applications engineer at Wolfspeed. Today in this video, I would like to showcase Wolfspeed's online simulation tool SpeedFit for industrial motor drive system simulation and show how Wolfspeed's 1200 volt silicon carbide MOSFETs help in meeting efficiency standards while enabling a smaller, lighter and more efficient end equipment such as heat pumps, air conditioners, industrial motor drives, servo drives and more. So let's get started. The user can navigate to SpeedFit from Wolfspeed's homepage by looking under Tools and Support tab and clicking on SpeedFit Design Simulator. If you're a first-time user, you would be required to input a couple of quick information before actually diving into the simulation. So let's start the simulation. As you can see, under the Applications tab, the user must first select the topology type. It could be AC-DC, DC-DC, or a DC-AC. As an example, if we look under AC-DC tab, the user has the choice to choose single-phase and three-phase topologies. The user can choose single-phase topologies like classical boost PFC or totem pole PFC, or three-phase topologies like two-level active front-end or multi-level active front-end topologies. For this example, I will try and simulate a motor drive inverter, so I will go ahead and choose a simple three-phase two-level inverter. Let's click on Next and go to the next tab. Under the next tab, Devices, the user is required to input system specifications such as input voltage, output voltage, and rated power. So for the rated power output, let us try and simulate a 20 kilowatt motor drive inverter. Input voltage, let us choose an 800 volt DC link. And for the output AC voltage, let us input a 400 volt system. The tool then lets the user choose between a discrete or a module based solution. For this particular example, I'm going to choose a discrete based solution. As you can see, the tool then outputs a list of suitable Wolfspeed devices for this application based on user-defined inputs. For this particular simulation, I will choose a 40 milliohm 1200 volt Wolfspeed silicon carbide MOSFET. As you can see now, the tool then lets the user input the number of parallel devices as well as the turn on gate resistance and turn off gate resistance. For this particular simulation, I will keep these default values and go to the next tab. Under the next tab, Circuit, the user should input the circuit parameters that are needed for simulations. For example, let us take one for power factor. For the AC frequency, let us have 50 Hz. For the switching frequency, let us choose 25 kHz to be outside the audible range. For dead time, let us take 100 nanoseconds. And for the load inductance, let us take 2 millihenry. This option actually enables the user to emulate a real motor and use the load inductance from a motor into the simulations. The next tab is thermal parameters. In this tab, users should input the thermal resistance between the case and the heatsink. So let us go ahead and enter 0.4 for this. So if you do not have this value handy, you can always click on this link and you can get a good summary of different thermal interface material and their thermal resistance between case and heatsink across different packages. For the heatsink model, the user has the option to choose among variable, fixed, and custom thermal impedance. For our simulation, let us go with a fixed heatsink maintained at a temperature of 75 degrees. Let's go to the next tab and click on Simulate to simulate our system. So SpeedFit is a Plex-based system, and the simulation takes just a couple of seconds to output all the results. And we can see that SpeedFit outputs results under three tabs: temperatures, losses overview, and losses breakdown. If we look under temperatures tab, we can see that for the device that we chose for this application, the maximum junction temperature is close to 118 degrees Celsius, which offers us enough margin from the absolute maximum rating of the junction temperature, which is 175 degrees for this device. Further, if we look under the losses overview, we can get the data for switching losses as well as conduction losses. In addition to that, we can have a look at the efficiency for this system, which is just over 99%. Further, it is interesting to note that in loss breakdown, we can actually see the parts which contributes to switching losses and conduction losses. For example, we can see that 37.67 watts of turn-on energy losses is what constitutes the switching losses, whereas this is the turn-off loss part of the switching losses. Similarly, for the conduction loss, we can see that what part of forward conduction losses, reverse conduction losses, and body diode conduction losses constitute the total conduction losses. In addition, on the right, we can see that we have all the steady state waveforms for our system: the load voltages, the load currents, the MOSFET voltage and the MOSFET current, as well as the junction temperature. So let us hold this result and try and simulating the system with a module in the second step. So let us go back to the device tab, choose module instead of discretes. Let us show all the devices here. And for this simulations, I will go ahead and choose this 32 milliohm FM3 Wolfpack module. Let's try and simulate the system with our module. So the simulation is complete, and we can see that for the module, the peak junction temperature is close to 126 degrees, whereas the efficiency is pretty close to what we got from for discretes, which is 99.03%. Also, we could see in the loss breakdown of all the switching and the conduction losses for the module as well. So let us go to the next step by clicking on next here. On the next tab, summary, SpeedFit generates a summary of simulation results for both of our simulations, for discretes as well as modules. In addition to that, the user also has access to all the waveforms for both of these simulations in this tab. The user is able to export all of this data in CSV format for post processing and analysis. This feature of SpeedFit allows the user to actually plug and play different Wolfspeed devices for their system and compare their performance. So I hope in this video I'm able to explain clearly how with Wolfspeed silicon carbide MOSFETs we are able to meet efficiency standards while enabling a smaller, lighter and more efficient industrial motor drive systems. I hope you enjoyed this video, and if you would like to explore more, you can visit our website and check out SpeedFit, our online simulation tool. Thank you so much for watching.